I think you can start when you want.
Okay, very good. Thank you, Sergio. So let's go on in the lecture series about Nucleon partonic structure, which, as you have seen, has close connections with the lecture that we've just heard, and we'll see that again later today. Now, last time I walked you through the essential ideas of how one establishes factorization in terms of parton distributions or generalized parton distributions. That was probably the hardest part of my lecture series. And the next part will be somewhat more relaxed. What I want to do is to show you two rather different things, just a few things about what we know about parton distributions and how we've come to know about it. And then I'll say a few words about event generators. That should take us about the first hour today. So let's start with parton distributions. As I explained in detail, parton distributions reflect the non-perturbative aspects of scattering processes on a proton with a hard momentum scale. And that means either you have some non-perturbative method to compute such parton distributions, and there is an ongoing effort to compute parton distributions using lattice QCD, but that would go far beyond the scope of this lecture for me to explain you that. But you should be aware that this is an ongoing effort. I think it's fair to say at present, the parton distributions that we know best from experiment, they cannot be produced with the same level of certainty in lattice QCD, and it will take much more effort for lattice QCD to achieve their accuracy. But in turn, there are also certain parton distributions which are very poorly known, for example, in the spin sector, and there lattice QCD can often be very helpful, even at the state where it is now. But what I want to speak about in the following is how can we extract parton distributions from experimental data using the factorization concept we've seen in the last lecture. So first observation in that respect is what we can compute in perturbation theory is the dependence of PDFs on the renormalization scale. Of course, more precisely, we can compute that dependence in the region where the scale is big enough such that alpha s is small, because this dependence here involves the Dirac splitting kernels, and they are computed in a series as a series in alpha s. So what is the principle of such PDF determinations? You have to choose data for observables for which you have a factorization formula. And the most important ones are inclusive DIS, always back to the textbook example, complemented by other processes like the Brillouin process, so producing a lepton pair either in the neutral current or in the charged current W case, the production of jets, both in PP and in EP collisions, and more recently at the high energy proton colliders, Tevatron and the LHC, you have top, anti-top production, and the list doesn't stop here. So one has to make a choice of which data one wants to consider. The other ingredient is to take a parameterization of the parton densities at some scale which you fix, and that's often called the starting scale. You can then, using the Dirac equations, compute the PDFs at any other scales, and notably at the scales where the experimental data is sitting, and which appear in the factorization formulae, one example of which I showed you in the last lecture. And then one performs a fit, often a standard chi-squared minimization fit, but there's also other methods in which you determine and optimize the parameters in your PDFs at the starting scale by such as to get the best agreement between the evolved PDFs in the factorization formula as they describe then the experimental data. And I should add, this type of enterprise has been pursued for many decades now. It started shortly after the Parton model was introduced, and by now it's a very mature subject. And one of the signs of that is that any modern determination of parton densities will come with errors. And since this is quite important in practice, I want to say a few words about what these errors are. Typically, these errors on the PDF or on the PDFs are obtained by propagating the error in the experimental data, statistical and systematic, to the fitted parameters. So it's the standard error propagation you have in fits. The data has uncertainties, and therefore the fitted best parameters have uncertainties. However, it's very important to realize that these are not the only uncertainties that one has when the PDFs are extracted. And there's a whole bunch of uncertainties that come not from the fitted data, but from the theory that you use. And part of that is already, well, you can say this is halfway between theory and experiment. First of all, you can have some bias from which data sets and which kinematic points in the data you choose to fit and which of them you choose to exclude. Certainly the perturbative order of the evolution and the orders used in the hard scattering cross-sections has an impact on the PDFs that are extracted. So they should be labeled with the order that is used to extract them. The factorization formula includes some other parameters necessarily, certainly alpha S, which you have to use for the evolution, among other things. And if one includes appropriate processes, you also need quark masses, the charm, bottom, and the top. And that is also a choice. Either you can take these parameters from other sources, for example, the particle data book, or you can try from the same data that you use to extract the PDFs to also extract these parameters. And both possibilities are being used in practice. Then there's fine details of perturbative calculations. How exactly are heavy quarks treated? How does one treat various types of free summation to all orders? Remember, I told you briefly about that in the context of Sudakov logarithms, and so on. And last not least, I emphasized last time that any factorization formula is an approximation. It has power suppressed corrections. And also here there are different strategies of how to deal with that. You can try and minimize the size of such corrections by taking only data with high enough scales Q. Now, in some cases, you cannot really afford taking Q too large, because otherwise you have not enough data left to be fitted. And in some cases, when one has to include data at lower Q for practical reasons, one might try and include some model for the power corrections, which might have its own parameters that are fitted. But all these details here have an impact on the outcome. And logically, they're not by construction included in the error propagation that I discussed in the beginning. Now, these differences are getting blurred to some extent in more recent times, because several of the parton fitting groups have started to try include at least a part of the theory uncertainty. And typically, these are the uncertainties from uncomputed higher orders in the cross-section formulae, for which we have this simple tool of scale variation, as I discussed with you before, to include these uncertainties in the errors that the PDFs are delivered with. So one has to take then a closer look of what the PDF errors include and what they do not. Now, this was a long description of what BUS does in principle. Let's take a look at typical outcomes.
Markus, excuse me.
Yes, you have a question?
Can I just a very quick question?
Yes,
You do
please.
not list the factorization scheme dependence, for example, or I don't see it in the list. If you
Yes,
use MS bar or something
yes,
else.
the list isn't is not exhaustive. There are different renormalization schemes, as I explained you in the first lecture. And likewise, there are some different choices for the factorization scheme. Remember, that is the choice of how much of collinear physics do you take out of the hard scattering cross sections, and how much do you leave in there. And all this makes a difference. But actually, when it comes to a scheme dependence, I would not call it an uncertainty, because once you've picked your scheme, you are quite certain what you're doing. Yeah. So in that sense, also this line here isn't really a source of uncertainty. What is a sort of uncertainty is that for any order that you are using, you have uncomputed even higher orders, and these give rise to an uncertainty. And when it comes to different schemes and different orders, you should just not compare apples with oranges, otherwise you are misled.
Yeah.
Very good, thank you. So here are some compilation of parton distributions as they are delivered to the community. These acronyms here describe the different groups that make these fits and extractions, and typically the last number is either the year where this was released or it's a version number. So these, the ones I'm showing you here, are the latest that are publicly available from different fitting groups. So here is plotted the x times the up quark density as a function of x on a logarithmic scale, at a reference scale of 2 GeV, which is a typical choice for the low scale. And you see certain features. There is a peak around, well, in the region of a third or so, and that is actually quite naturally physically. You would expect that an up quark in the proton likes to take about a third of the proton's momentum. That's the most naive picture you would get if you think of the proton as being made of 2 up and 1 down quarks. But of course, that picture is far too simple. But this peak here, in a way, remembers that there is at least some truth to that very simple picture. Another thing you see, if you look more closely, is that the different parameterizations in this case agree rather well. I put them in 2 different plots because otherwise it would be come too messy, but left and right show the same thing. But you see also some of them have much smaller errors than others. And there one has to be careful and look into the paper. Why is that? In fact, in this specific case, the very small error that is assigned in this fit here is not because the fit used much more data or much better theory. It comes out of a more restrictive parameterization of the starting distributions. And we'll see that again in the next slide. So the fact that these errors are smaller actually comes from the fact that the ansatz was more restrictive, or you could rephrase it as saying that certain additional hypotheses were made that were hardwired in the fit, and therefore they don't show up in the errors. So these things are important to realize when you want to really assess how well do we know these PDFs. Yeah, and I've emphasized that again here down in the text. I made sure that these plots here compare apples with apples as much as possible. All the PDFs are taken at NNLO, and all the error bands correspond to 68% confidence level as prescribed by the fitting groups. Now, let's look at the strange quark density. And here you see, oh my goodness, whereas here everything looked fairly clear, well, that's not really the case here. So there is huge differences between the different fitting groups, also concerning, again, the size of the error bands. And here you see very clearly that the error band of the Hera PDF fit certainly doesn't give you a complete idea of the uncertainty on this distribution. In fact, it comes from the fact that the Hera PDF fit uses only DIS data. That was a deliberate choice because actually the fitters here had their hands on their own data, so they understood best of everyone in the world the systematic uncertainties of the data, and DIS has a very good theory behind it, and that was the name of the game in this fit. However, by DIS alone, you cannot extract the strange quark density and distinguish it from up and down quarks. So in order to get a fit, you have to make an assumption, and that was done in this type of fit, namely just by setting at the input scale the strange quark distribution proportional to the C quark distribution in the light quark sector. I forgot which of the two possibilities here was taken. And if you make such an assumption, clearly the fit is more restricted, and that is what gives these small error bars. So if you want a more global picture, it's always a good idea to look at different contemporary parton distributions. And if you just do that, you see that, well, apart from some regions in X, you really don't know what these distributions are with any reasonable certainty. Now, these plots were at the scale of 2 GeV, and notice the scale of the size here was going up to 1.2. Now, if I plot these same distributions evolved to a higher scale, which I took to be 90 GeV, which is what you would probe in the production of a Z boson, now the scale goes up to 4. So what has happened is that the evolution to higher scales has produced us a very big amount of partons which have a small value of X. And that's easy to understand if you think of what the evolution equations reflect. They reflect that if you go to higher scales, a quark can radiate a gluon that can radiate another gluon, and in the end, such a gluon can split into QQ bar pair, which is what you see at this upper end, because this comes out of a cascade of splittings. Of course, the momentum that a single part of that cascade is carrying gets smaller and smaller. Another important thing you see here is that the size of the error bands has decreased compared with the error bands at the starting scale. That is a generic feature of these logarithmic evolution equations. And it is, by the way, also a feature of the running of alpha S on the quark masses. If you just look at how these differential equations work, and in the case of alpha S, you can even write down the analytic solution, as I showed you in the first lecture, then you just see some uncertainty at a small scale. If you go to higher scale, the relative uncertainties tend to shrink. So that's just a mathematical feature of the evolution equations. Another thing you see if you compare up and strange quarks, so this is for up, this is for strange quarks, is that small x, they all become very similar. Whereas at low scale, that wasn't the case at all. And that is again a feature of evolution. As I just told you a minute ago, the small x quarks here are the result of emitting gluons many times and then splitting into a quark-antiquark pair at the end. Since that splitting doesn't care about the flavor of the quark, that explains why you get something very similar here. So, also again, the relative uncertainties have shrunk quite a bit for the strange quark densities, but you still see some remembrance of the fact that they were very much very poorly known at low scales. The last parton I want to discuss here is the Gluon distribution. Again, this is the distribution at 2 GeV scale. Now for the quark distributions at this scale, the maximum values in my plots was 1.2. And here I need quite a bit a higher value. It goes up to 6. And that means that for values of x, if you look a bit more closely, roughly starting at 0.1, the gluon distribution is much, much bigger than the quark distributions. So that's something to keep in mind. And that's, I think, one of the basic things we have learned about the proton from studying parton distributions is at small momentum fractions, gluons are the most important parton type. What you also see is that, well, precisely in that region, the only thing that different fits agree about is that the distribution is somehow large. But exactly how large is again very poorly known. And that has a good reason. There's just not much data at all which would constrain the gluon density at such a small value of x. And the main reason for that is in turn that what really pins down the quark distributions at low x is the data for the deep inelastic scattering. And I've shown you a plot of how exquisitely good that data was from this F2 structure function last time. However, to leading order, that structure function tells us about quarks. And it tells us about gluons only at order alpha s, or via the coupling of gluons and quarks under evolution. That's a subleading effect, and that reflects itself in this much worse known situation here. Again, if you go up to higher scales, the error bands shrink, and you see that the overall size of the gluon density explodes even more strongly. This is by a factor of 10 and more compared with the quark case. And also that is understood because if one looks at the evolution equations with their splitting kernels, the splitting kernel for gluons has a bigger size than the one for quarks. And that reflects the fact that gluons carry a color octet charge, which is bigger than the color triplet charge of quarks. So a lot of the qualitative features of this can really be understood from QCD. Now here is another plot that deals with the strangeness, and that illustrates that the strangeness is really one of the worst known parton distributions in the unpolarized sector still. This ratio plotted here is the sum of strange and anti-strange divided by the sum of what is sometimes called the light C-quarks, up and down anti-quarks. And the uncertainties in this particular analysis for that ratio are quite large over the full region of X. This is at a low scale of 1.9 GeV squared. And here are comparisons for this at low square, Q squared, this at high scale for the prediction of that ratio at a certain value of X, not the same here and there, from different fitting groups. And even here you see that there is really a wide range of results. And that, again, the error bars of an individual fit typically do not reflect the spread of values and errors if you look at different analyses. This was for unpolarized parton distributions. Now, Barbara, in her lecture today, has shown you that, of course, that's only a part of what we can study in parton distributions. There's also polarization. And the PDFs for longitudinal polarization, they have been studied experimentally also for a long time. And here is a comparison from a recent analysis from 2000, again for different quark flavors. This is for the polarized up, polarized down, polarized strange, and polarized gluon. Polarized in this case means these are the differences of the density for a positive helicity parton minus the density of a negative helicity parton. So this is allowed to be negative because it's a density difference. And that's what you see, for example, here. So generally, even for the up and down, the errors are bigger than in the unpolarized case. And that just reflects the fact that there's not so much and not so high quality data for polarized collisions compared with the unpolarized ones. And of course, if you have less and less precise data, you cannot get as precise results for what you extract from them. Also, much of the available DIS data is at lowish Q-squared, especially for the spin case, and that gives you extra troubles. Bigger, higher order corrections because alpha S is bigger, and more uncertainty from higher twist. So you see, especially for the gluon here, well, frankly, there's a lot of uncertainty. And a collider like the electron-ion collider that's now being planned in the United States is aiming to remedy that in a very strong way by having polarized collisions between electrons and protons at high energy, which will allow one to cover larger values of Q-squared and a broader range in X. That will hopefully bring this picture somewhere closer in quality to the picture we have for gluons. For strangeness, it doesn't look so bad here, but that's because this here only compares a certain subset of different fits. And a more comprehensive subset of fits is shown here. These fits are by the same group, ABC, but they differ by the hypotheses that were made for the relation between strange and non-strange quarks. And you see, depending on the hypothesis you put into your fitting function, well, you get more spread than you probably would like. But that's the state of knowledge. And the only thing that you can say is that compared with the light flavors up and down, the overall value of the strangeness polarization is small. And that is, I think, about the only robust statement we can make at this point in time. So now for something completely different, just happens to fit in the same set of slides. I want to say just a few words about what I would call the general purpose event generators, mainly Herwig, Pythia, and Sherpa. These are built to describe a very large range of processes in high energy collisions, and they are for many experimental analysis, say at the LHC or at other high energy collision colliders, they are the workhorses. There's barely a physics analysis that one could do without some event generator, be it only for understanding and estimating the experimental uncertainties. Now, what I will say, the following does not apply to all generators. There are many more event generators. They often have a very specialized scope rather than being general purpose. And often that specialized scopes allow them to have a very specialized and precise approach in that smaller scope. So not all of the existing generators fit in what I will describe now. What I will describe now is very closely tied to the factorization approach that I explained you yesterday. So one can characterize the general approach of these generators as starting in some way from the physics picture and from the predictions of a factorization formula. So let's again take the example of producing a Higgs boson and a gluon and anything else. And a gluon, of course, means in the hard part of the scattering. So this is what then is computed just as you would compute it analytically by computing the Feynman graphs. Perturbation theory is good at the short distance regime here. So what you need on top of that hard scattering cross-section or hard scattering matrix element, it's often called, you need, of course, the flux of the incoming partons, and that is given by the parton distributions. So precisely by the quantities I discussed in the slides before. Now, one doesn't stop here. On top of this, any strongly interacting particle can radiate more strongly interacting particles, and that is described by what is called parton showers. So in particular, parton showers represent the region of collinear and soft radiation from partons And if you remember the lecture about D plus E minus annihilation, it is the collinear and soft radiation region where radiation is enhanced because particle propagators become big. So this is the important region of radiation, which you want to not describe in a fixed order way, because in a fixed order way, you would have alpha s times a large logarithm. Instead, you want to carry this to high orders. And parton showers can do that because they just approximate radiation in the collinear and soft regions in such a way that you can iterate it for 1, 2, 3, and more emissions. Of course, that can only be done in a region where you are still at a scale that is large enough for alpha s to be reasonably large. So these parton showers will typically stop at some low scale of around a GeV or so, because below alpha s is so big that this approach is no longer reliable. And that's some part of the physics. If you have a proton-proton collision, we have these spectator partons. And remember, when I discussed factorization for Drell-Yan yesterday, I alerted you already that physically there's no reason to expect that the spectators in your initial protons would not interact, and in fact they do. So the Monte Carlo generators actually include that kind of physics by making a model. And why is that done? Well, I forgot to specify, but I should have. The idea of a Monte Carlo event generator is in a way opposite to what the factorization formula is doing. The factorization formulae that I discussed are for inclusive processes where you always have something produced in a hard scattering, which you're allowed to specify, plus anything else. And that anything else is important to even have the factorization formula. Instead, a Monte Carlo event generator wants to describe fully specified events. And that is the opposite of saying plus anything else, which I won't tell you anything about. So clearly, if you want to describe what the anything else looks like in detail, you have to go beyond factorization and beyond the physics of the factorization formulae, and you have to include in particular such spectator interactions to get anywhere close to measurements and physics. And finally, so if this kind of spectator interactions happens in a region of a few GeV, you can still model it with perturbation theory, and that's what's typically done. But eventually, if you go from partons to hadrons, because that's what you see in a measurement, you have to include a model for hadronization. And there are different approaches to doing that, which are just sort of sketched in a very fluffy way in this cartoon here. But the different generators here, they actually have models for hadronization that on the one hand are very advanced because they've tuned to many data. And on the other hand, there's really a lot of physics imagination that goes into these models. So they're by no means naive or so. And it is just one has to realize they are models. And any model typically has its limitations. And that's a big part of the research that goes into these generators. So here's a general summary of what I've discussed up to now about parton distributions and about Monte Carlo event generators. And if there's any question about this, I'd ask you to ask it now, please.
Yeah, can I ask a question?
Yes.
I was interested about the part when you when you talked about the non-perturbative methods to compute PDFs and in particular lattice QCD. And
yes.
Can you comment something about the tension that seems to be in the determination of the tensor charge by lattice methods and by the integral of the transversity, the first moment, the Mealy moment of the transversity?
That's a very specific question. I think generally one has to look at the uncertainties on both sides. What are the uncertainties in the lattice calculations? And what are the uncertainties in extracting PDFs from data? And for something like the transversity PDF, that's the PDF for transversely polarized quarks, that's about the most difficult type of parton distributions one can try and extract from experiment. So I wouldn't be ready to make a detailed comment on that, except that in a way it's not surprising that it is in that area that the errors of individual approaches are biggest and that they might not agree. And then one has to try and push on one hand, try and get more precise data, but also get data that you have a good theory to analyze. And in lattice calculations, there's also many systematic uncertainties that one has to work hard to overcome. And working hard for lattice calculations means, on the one hand, often you have to have many more much more computing power and computing time, but also you have to invest in the algorithms and in the way that you try and extract physics. So that's a very generalized answer, but I'm afraid I can't really say more at this point here.
No, okay, yeah, I was only curious. Thank you very much.
Any other questions?
I have a question. So I understand that you haven't mentioned this before at all, but maybe this is a stupid question, but we're always talking about valence quark and C quark. Yes. And I'm wondering how the experimentalists, how to say, distinguish between those two. How do they?
That's a very good question. Thank you for asking that.
Okay.
In fact, there's two notions of valence quarks and C quarks, and it's very important to not mix them up, although they are related. So I can try and write that down. Can I? Yes, I can try and write that down here. Ah, no, the writing doesn't work here. One definition of what valence and C quarks are, and that's the definition that's typically adopted in the context of plots of PDFs and fits of PDFs, is valence quark means the quark minus the same antiquark. So it's a simple name. The valence the U valence distribution is the difference of U of X minus U bar of X.
Okay.
The C quark distribution for up quarks would then be called the anti-up distribution. Likewise for the for the B quarks. For strangeness, it's a bit different in the nomenclature, because you would call both strange and anti-strange quarks as you would label them as C quarks. So then what you call the C quark for strangeness might include the sum or just half of it. That's a matter of definition, and one needs to look what people adopt. The physics idea behind these names is that one would in some way start from the proton as being made up of an up and another up and one down quark. And this is what you could call the valence quarks. And in fact, that name survives also in when you have this Fock state picture that Barbara discussed before. You would call the up-down state the valence Fock state of your system. And then if you think about radiation and interactions, any quark can radiate a gluon, and gluons can split into quarks, antiquarks. So you get all the multi-parton states, and the quarks or antiquarks that you get out of this branching process, you would call the C quarks.
Okay.
So that is valence and C as a dynamical picture, whereas in the context of labeling parton combinations, valence is quark minus antiquark, and C is the antiquark, or in the case of strangeness or higher, couldn't do the same discussion for charm, it would be the quark and antiquark part, because none of this is part of the valence Fock state. So
Oh,
the two
okay,
notions are related, but they're not identical. And sometimes in discussions, there's misunderstandings because people are not aware of that difference. So it's good to know that there's these two meanings.
Oh, okay. Thank you. Thank you.
My pleasure.
Markus, can I see again the last but one slide, the one with the ingredients in the Monte Carlo?
This one?
This one.
Yes.
When you at the end mention multi-partner interactions in this picture, you
Yes.
mean here they are soft multi-partner interactions in the underlying event, or you are inserting, you are speaking about everything?
Depends a bit on the detailed implementation. I know that Pythia for sure, and I think also Herwig, allow for such interactions to produce something very massive.
Okay.
And it could be even, in the case of Pythia, it could be a second electroweak interaction. So you could have two spectator quarks that annihilate and make a Z boson. Yeah, so in that sense, that is what one would then call double hard or double parton scattering.
And in that case, you don't have a PDF, you have a double PDF.
In that case, you need something which tells you not about one quark being extracted, but about two quarks or two partons being extracted. Yes, and I'll speak about that in my last lecture.
I know, thank you. Thank you.
On the other hand, what is much more important for, let's say, generic final states is when the secondary interactions are QCD interactions, because then you have the strong coupling rather than the small alpha electromagnetic or weak. These strong interactions could produce you another dijet of several 10 GeV. At the LHC, you have so much incoming energy that another dijet of 10 or 20 or 30 GeV is perfectly possible kinematically. But it could also be a dijet, so to speak, of 1 GeV transverse momentum. So at that point, the Monte Carlo generators have to make some extrapolations of the perturbative calculation to low scales, and then some model of what happens at very low scales when you wouldn't speak even of partons, but at low momentum pions or protons that you see in the final state. And that is then less and less tied to perturbation theory and more to non-perturbative ideas and degrees of freedom.
Thank you.
So I would say to have a model for the low energy activity is absolutely essential for such a generator to get global features of the observed events right. To additionally allow for two very hard interactions is only important if one looks at very special final states.
Right.
Okay, then let me maybe switch to the next part of the lecture, and then I have to, for this I have to switch slides. So let's see if I can do that. Share the other set of slides. So do you see the slides for part 5 now, GPDs?
Yes, we do.
Very good. This is going to not duplicate, but complement what Barbara has told you just an hour ago. In the beginning, there will be some overlap, or mainly because I also wanted to get the notation clear, but we can run through that rather quickly, and then I will speak about some things which Barbara didn't have time to cover in so much detail. So first of all, we have, of course, to define what a GPD is. Barbara went through that in great detail. Let me just re-emphasize the operator that defines a generalized parton distribution is exactly identical to the one that defines an ordinary parton distribution. All that changes is that for an ordinary parton distribution, you have the same state in the bra and in the ket here, whereas for a generalized parton distribution, these states can differ. And they can differ by, well, almost anything you like. They can differ in their momenta, they can differ in their spin state, they can even differ in their particle content. So you could have a proton state here and a neutron state there, or whatever else you can make a process to measure it in. So let's briefly look at the kinematic variables, just to also set the notation. Barbara called this X, what I call X, in Barbara's slides is called X bar. That's sometimes useful to distinguish it. Because in fact, if you remember last lecture, I had an asymmetric way of parameterizing the X values. X in my last lecture was referring to the incoming proton momentum. And I did that in order to have a more natural connection to the case of inclusive DIS, where you compute forward scattering. And in that case, simple kinematics shows you the outgoing parton if that has momentum fraction X with respect to the incoming proton, the outgoing parton. Then the returning parton has momentum fraction X minus X Bjorken with respect to the incoming proton. And that's what gives you this factorization formula that I had on my slides last time. If you want a more symmetric treatment of the initial and final state here, you go to this set of variables where the momentum fractions are with respect to the average proton momentum before and after the scatter. And also you take the Xi to be defined in a symmetric way compared with the initial and final state. Now, which of these parameterizations is more useful depends on what you're looking at. This here is in particular useful if you want to make symmetries of these distributions apparent, because some symmetries are easy to see with these coordinates and a little bit more arcane to see in those. But as usual, a choice of coordinates or of variables is not unique, and all you have to minimally do is to know what kind of choice you're talking about at a given time. So in particular, if you want to switch between X Bjorken and Xi, you just have a simple formula that relates them. Another important remark, which Barbara has also made, I believe, is that the invariant momentum transfer T depends on the longitudinal part, which is expressed in this Xi variable here, and the transverse momentum transfer in this way. And that's important for this impact parameter picture, which I will rediscuss in a moment. Let me skip over this. Barbara has explained you in very nicely and in detail that you have these different kinematic configurations. Remember that for ordinary PDFs, I had discussed the region of positive X and of negative X. Xi was 0 in that case, so the middle region didn't exist. But even at Xi equals 0, you have this quark emission or anti-quark emission regime. Everything else, I think, has been discussed. There is a spin discussion, the spin dependence at two levels. There is a dependence on the proton spin, because as I said, it doesn't have to be equal in the two states here. And that is parameterized in a certain way by using these proton level spinners and two functions. And there is a spin dependence at the level of the partons, which means you have different gamma matrices in this operator here. So the ones with a tilde on top are typically for longitudinally polarized partons. And then there's also what I haven't written down here, the distributions for transversely polarized partons, which carry an extra subscript. Also, very, very important is the fact that, as I showed you last lecture, and as you will see in more detail in an exercise, taking a Mellin moment at the operator level of these operators here gives us a local operator. And then the matrix element of a local operator between identical states, which you would have for PDFs, gives you what is called a charge. And giving taking a matrix element of that same operator between different momentum states gives you what is called a form factor, which depends on the invariant momentum transfer between the two states. And taking that transfer to be 0 gives you back the charge. So in particular, for the lowest Mellin moment, we get the vector current and the associated electromagnetic form factors, of course, depends on how you where you put the charge. Typically, with the superscript Q here, you mean the contribution of the current without the charge factor, and that has to be put on top. So I want to just briefly give you also some complementary information about the impact parameter, also because it will be important in later parts of the lectures. As Barbara already mentioned, if you want to go from a momentum eigenstate, which I can parameterize in terms of light cone coordinates, that's perfectly legitimate. If I want to have a hadron state that is localized in the transverse plane, I just take a wave packet in the transverse momentum by taking this Fourier transform. And one can show that formally these are eigenstate of a two-dimensional position operator in the plane that is perpendicular to the third direction. For the third direction, I keep this representation in terms of plus momentum. So this is a mixed representation, partially in momentum, partially in position space. This allows me to exactly localize a hadron state in 2 dimensions. And from general lectures of field theory, you might remember that if you try to do the same thing in all 3 spatial dimensions, in a relativistic theory, that's actually not possible. In other words, there is no 3-dimensional analog of a position operator to which a 3-dimensional wave packet would be an eigenstate. So there's some deep field theory behind these things. In fact, if we speak about parton distributions, it is actually very desirable to openly localize in 2 dimensions, because the third dimension, where we keep momentum, allows us to keep the contact with the parton model picture. Because remember, for the parton model picture, it was essential that your hadron moves fast in 1 direction. That allowed us to neglect minus momenta compared with plus momenta and such. If you were to take a proton state at rest that is somehow localized in all 3 spatial dimensions, you could no longer say that this moves fast in any sense. So it's just not a useful way of thinking about processes and the physics picture where you want to speak about partons. What Barbara also explained, by the way, I should perhaps mention that in Barbara's lecture, the normalization of these position eigenstate is taken in a different way than I use it here. The states, as I defined them here, actually have a norm that is infinite, that comes from just having infinitely extended wave packets here. One can try and prepare that with a normalization factor, and that's what you find in Barbara's slides, just to make sure that you have to be careful when you compare equations. Now, what does this localized position mean for a proton state, which after all, the proton is not point-like? It means it is the center of plus momentum of all partons in the proton. And also Barbara explained that very nicely to you already. So just like you would define the center of mass belonging to Galilean invariance in non-relativistic theory, you have this center of plus momentum, or short center of momentum of a multi-body state here by weighting the position of each part of the system with its plus momentum and taking the whole thing normalized. And that is actually important in what follows. Now, here is the operator that appears in a GPD, as we've discussed it many times. And what I was about to show you was that if you take the longitudinal part of the momentum transfer, so this xi variable equal to 0, so you have the same p plus here and there, and if you sandwich this operator between our hybrid position momentum eigenstates, then what you get is you get a delta function in the position. That means the positions here and there have to be the same, and you get the Fourier transform of the GPD defined in momentum space and evaluated at xi equal to 0. I was about to show you that in a little calculation, but it turned out that it's actually an exercise in Barbara's lectures. And of course, I cannot possibly do your homework for you. So you'll have a chance to see that by yourself. So here's the upshot again of this discussion. Staying at xi equal to 0, we can define what is called an impact parameter dependent distribution, for which we have a nice density interpretation in the same way as we have it for PDFs. This is the probability density to find a quark at longitudinal or plus momentum fraction x and at a distance of b from the center of the system. And with this, I think, well, I can maybe still discuss the rest of this slide and then we make a break. If you have such...
Sorry, I was wondering if I could ask a question.
Yes, please do.
So obviously the impact parameter B and the delta here, which represents the momentum transfer, are Fourier conjugates. That's correct?
Absolutely.
So why does one choose to use the T and Xi basis as opposed to just the two transverse components of delta when, but often when we're talking about GPDs, for example? I mean, presumably they're equivalent, but we just do this for historical reasons that I'm unaware of, or I'm not sure.
Well, the delta here is this two-dimensional vector with an x and a y component if the longitudinal direction is along z. Why we make a distinction between a longitudinal and two transverse directions here? Well, part of the answer is has to do what I discussed on this slide. A parton model picture applies in a frame where the proton moves fast, and that direction of movement selects what I call longitudinal. I can take another point of view and ask, where can I learn something about such quantities? And that is in exclusive processes, which I'll discuss a little bit after the break. And in an exclusive process, that is a collision if you go to the center of mass of that process. And in a collision, you always have one longitudinal direction singled out, and that is the direction along which your two two particles approach each other. So it is the process that selects a longitudinal direction, and that's why it is quite natural to take a set of variables in which you don't have an explicit three-dimensional rotation invariance, because anyway, the physics you're looking at is not having that invariance. The physics you're looking at has at best an axial invariance of rotations around your longitudinal direction, unless that invariance is broken by singling out a transverse direction in the measurement. Does this help a little bit?
Yes, that's very helpful. Thank you.
Good. So if you have this two variable distribution here, one thing you can do is to look at averages as a way of sort of reducing information if you wish. And the average b squared, defined in this way here, just by the way of how Fourier transforms work, you can easily see it is, you get it from the momentum space quantity by taking the derivative with respect to t and evaluating that at t equals 0. Barbara had the same the same definition. If you, in addition, integrate over the x variable in the numerator and the denominator, then you get the corresponding derivative of the elastic form factor that is related to your distribution h here. And let me see what the next slide is. I think this is a good point to break. Sergio, how long would you like us to break?
You decide, maybe 10 minutes at, I don't know, what time is it? Maybe at 25, is it okay?
Okay, yes, let's say we reconvene at 25 past. So let us resume the lecture at this point.
Very good.
So I would like to briefly show you a bit how this interpretation changes if one goes to non-zero values of Xi. It becomes a little bit more complicated, which is not surprising, but the important point to realize is that it is still possible. So if one works through the same kind of exercise as I showed you here, or as I did not show you here, but as I stated, with plus momenta that are different between the initial and final state, cranks the handle, then one reaches the following picture. If you want to interpret an impact parameter GPD that is a Fourier transformed GPD at non-zero values of Xi, you have to again, which is not surprising, distinguish between this D-glub region where you take out a parton and put it back, or the ERBL region where you probe a quark-antiquark pair coherently. So in the first case, you find that this impact parameter B is giving you the distance between the center of momentum of the proton and the point where the parton is extracted, or where it is found, but not quite. Rather, there is some multiplication factor to be for this distance, which depends on Xi. Which means you still know what the distance is, only there is a little bit of a rescaling. Rather interesting is that the rescaling depends or differs between the initial and final state. So in other words, the center of momentum of the proton as a whole is not the same in the initial and final proton state. And that is something one can actually understand. Namely, this is the center of plus momentum. So it is determined by the positions of all partons weighted with a momentum fraction. But we take out a parton with a certain momentum fraction and put it back with another momentum fraction. So the weight of that parton in the overall average changes. And just as the center of momentum of your bicycle wheel changes if you take out a spoke and replace it with a spoke that has a different weight, the center of momentum of the proton before and after this is not the same. And the same happens in perhaps even a more obvious way. If you take away a quark-antiquark pair with total momentum fraction 2Xi, then the center of momentum of your system changes by a determined amount. So other than this complication, it remains true that by Fourier transforming impact parameter GPDs at non-zero skewness Xi, you still have a very clear and nice representation of the physics in terms of distances of the probed object from the object that you have as a whole. Let me skip over the next slide. You can look at it offline if you wish. There's always a danger of comparing apples with oranges. So here I would like to make a few remarks in that direction. As Barbara explained you and showed you in detail, you have the elastic form factor, the Dirac form factor, and from that you can extract the average impact parameters squared for the distribution of quarks minus antiquarks. That's of course not surprising. The difference of quarks and antiquarks is what the electromagnetic current is seeing, weighted by the electric charges. And this here is the number that you get if you use the actual data. I haven't put here an uncertainty. There is, of course, an uncertainty, but it is very small. Then there is, if you look, for example, in the particle data book, there is a number given for the proton radius or the proton charge radius. That is defined to be extracted from the electric form factor, which differs from the Dirac form factor by a magnetic term, and that is why you would have this number here. But even more important, this is not the number you will find in the particle data book, because the charge radius as it is defined there corresponds to a three-dimensional radius in this interpretation, which Barbara also discussed, whereas here you have two-dimensional radii, which is also why I call them impact parameters squared. And that just means that between the two numbers, there is a difference between a factor of 2/3 in the squared quantities. And that is just something you shouldn't overlook when you interpret the numbers. And I'm emphasizing that because it's sometimes done. There is also data, although much less precise and much less abundant for the axial vector current form factor, that in terms of parton distributions corresponds to the sum of up and anti-up minus the same for down plus anti-down. And looking at a certain extraction of this form factor already a while ago, that gives you also an average impact parameter, which interestingly is quite a bit smaller than this number here. So although individual uncertainties are there, I think it's beyond doubt that this is a smaller number than what you have in the electromagnetic channel. And another number one can look at is from J-psi photo production that's been measured at the Hera Collider. I'll come a little bit back to that in a moment. One can extract something like an average impact parameter of the generalized Gluon distribution at typical values of x equal of 10 to the minus 3. That's just some broad average number. And that, depending on the measurements one looks at, is in this ballpark. So again, it is significantly different from the number that you have here for quarks, which, since it's a form factor, is understood to be integrated over all x values and not differential in x. Something I also wanted to just mention and briefly show is that there are lattice QCD calculations for the lowest Mellon moments of GPDs, already some years old. This uses this connection between Mellon moments and local operators, as both Barbara and I have discussed. And if you rewrite that in terms of this impact parameter distribution, this is what you get. You can then compare these form factors for the currents with no one or two derivatives between the quark fields, and from the results you can extract certain radii. Now the picture here shows the radii extracted, or the average impact parameters extracted for different pion masses, because this was one of the quantities that this lattice calculation was actually varying. So an important pattern you see here is that the distance becomes smaller if you have more derivatives, and that means if you have a higher weight in x. And that means the decrease of the average impact parameter with x is quite visible from these simulations. And that is exactly the same trend that Barbara has shown you from a totally different source, namely the analysis of DVCS data in different kinematic regions. So you see that, I think this is very gratifying. The same type of qualitative behavior is seen in totally different contexts using totally different methods. And to that extent, we have a consistent finding and picture. Now, last time we looked at detail, and also today earlier, at the fact that parton distributions evolve with the scale. And of course, the same must be true for generalized parton distributions. And that's what I want to briefly discuss here. You have then a generalization of the D-Glab equation, if you wish, which looks a little bit different in its form here. You have now a kernel that depends on two momentum fraction and this skewness variable xi. What it does not depend on is the momentum transfer t, and I'll explain you in a second why that is the case. Excuse me. Just as in the case of the PDFs, the flavor singlet, that is summed over all flavored Q plus Q bar combination, mixes gluons and quarks, also in the GPD case. So it's nothing new, it's just the same thing again. Another important statement is that the distribution E evolves in the same way as the distribution H. And if you remember the definition, they are defined by the same operator at the quark level, but they represent different combinations of the proton polarization. So why is this kernel the same for different proton polarizations, and why does it not depend on T? That is because one can understand the scale evolution as a property of the operator which defines the GPDs. So you can derive, in fact, from this operator, which also has a scale dependence, which comes from the fact that you have to renormalize it, as I explained last time. You can write down an evolution equation in the renormalization scale of this operator, which then obviously depends on the position, not on momentum, independent of which type of states you take a matrix element with. And from that point of view, it's then clear, if you take the matrix element, then the evolution of the operator does not care about any momentum transfer between the states or any spin degrees of freedom of the states in the matrix element. And that's what comes out of an explicit calculation. So as Barbara also said already, how this evolution works and how it looks like differs between the D-Glab and the ERBL regions, which are these two partonic regimes. In this regime here, this works pretty much like the D-Glab equations for normal parton distributions. By radiating partons as you go to higher scales, the partons tend to lose momentum. So the parton distributions, as you go to higher scale, tend to be shifted towards smaller values of x, exactly as we've seen it for PDFs in the first part of today's lecture. Rather differently, if you look at this QQ bar system, well, you don't radiate anything away in that case. What you have is you have a gluon exchange between the quark and antiquark that you probe. And that gluon exchange tends to equalize or make the distribution more symmetric in one and the other, which intuitively is also not surprising. So it is the same physics that is responsible for evolution in these two regimes, but the way it works phenomenologically is quite different, and that is because you're looking at different momentum configurations. And by the way, the names of these two regimes come from the names of the evolution equations that were discussed much before GPDs were considered, either D-Glab for normal parton distributions or the so-called ERBL evolution equations, which had been written down long time before GPDs for what Barbara also mentioned, namely the distribution amplitude of a meson for its QQ bar state, which from the point of view of the operator that probes this QQ bar state is again exactly the same here and there. The only difference between these two quantities is that here you would take a matrix element between that of that operator between a meson state and the vacuum, whereas here you take the matrix element between one proton state and another proton state. And since evolution is a property of the operator, not of the states, it's not surprising that the evolution here and there has the same form. One can also see how what this implies for the evolution of the impact parameter densities that we've discussed before. So if evolution is local in T, then of course, that means the kernels do not depend on T. If T is just a sort of a label in this evolution equation and plays no role other than that. The same is true if you perform a Fourier transform with respect to that label in B. And if you take the special case xi equals 0, then this xi-dependent kernel must somehow reproduce the parton, the D-glab kernel for the ordinary parton densities. And then this is what you get. Not surprisingly. It's just the same equation you would have for a normal parton density. The NS here means it's here I'm specializing to a flavor non-singlet combination, like up minus down, such that I don't have to write down the coupling, the mixing with the gluons. If I look again at my average impact parameter here, since the numerator and the denominator are scale dependent, so is the average impact parameter. And it's easy to derive from this equation here an evolution equation directly for the average impact parameter as a function of x. And that has the form that's written down here. It's have the same splitting kernel. Then it depends on the difference of this impact parameter at two different x values, and it involves the full z-dependent but B integrated PDF impact parameter distribution. So that is again an important thing to realize. If we resolve partons in an experiment and speak about their distribution, it is a scale dependent information. And also the information where in the proton I've seen the parton is a scale dependent information. And I have to take that into account. Now let me speak a bit more about the processes in which one can access GPDs. That has again to do with factorization. Barbara has told you a little bit about it, so I can just give some complementary information here. One big group of processes is involving two electromagnetic vertices. Deeply virtual Compton scattering I discussed already quite a bit. If you go beyond leading order, you have, like in ordinary DIS, not only quark but gluon distributions that are involved. And another thing you can do is, instead of having a virtual photon in the initial state, you can take a real photon in the initial state and provide yourself with a hard scale by having a virtual but now time-like photon in the final state. And just as you would do it in Drell-Yan, the finite, the high virtuality photon can then decay into a lepton pair, which is measured in the experiment. You can combine the two cases by having a space-like off-shell photon in the initial and a time-like off-shell photon in the final state. So then the process is production of a lepton pair in lepton-proton scattering. That's sometimes called double DVCS. The other big class of production processes involving GPDs is producing a meson at high Q squared from a high Q squared photon, or if you have a heavy quark meson like a J psi, that provides you a hard scale, so you can allow the initial photon to have a small virtuality. And that's this J psi photo production measurement I mentioned before. The benefit of going to small Q squared in that case is that the cross section is much better, and therefore the statistical accuracy of the measurement is also exquisite compared with the same measurement at large Q squared. So a little bit more about the description of DVCS and the step from going from measured DVCS to GPDs. There are amplitudes which are populated in the Bjorken limit, and another way of saying that, they are populated by twist 2 distributions like the ones we're discussing here, and corresponding to the 4 GPDs per parton species we have for unpolarized and longitudinal polarization, we can write down 4 photon helicity conserving amplitudes, which have the same dependence on the proton spin as the GPDs have. So the difference between these H's here is these are defined with respect to the proton and a quark anti-quark operator. These quantities here are defined with respect to the scattering amplitude for a process. Since they are defined with the same type of proton spin dependence, and these quantities here are called Compton form factors, they can be written in terms of the GPDs in the Bjorken limit by this kind of hard scattering kernel, which in C and X looks like such, weighted with the electric charges, and the GPDs themselves. So this is how a factorization formula would look like for the amplitude level in the GPD case, that is for an exclusive reaction. And notice the difference with a factorization formula, for example, for inclusive DIS. In that case, you have a parton density on the right-hand side, and you have a cross-section on the left-hand side. To go from these amplitudes with a certain spin dependence to the cross-section, you have to square the amplitude, and that is why in the cross-section of DVCS, you have squares of GPDs that come in. Now, what's the good thing about DVCS and its close relatives like time-like Compton scattering? Since it's a 2-photon process, it has a very high theoretical accuracy because people have been able to compute the next to leading order, that is the alpha S squared corrections to this simple handback graph. And people are working even on the next order correction. So the theory is very precise. Also, it's very close to what we know to inclusive DIS, and we know a lot empirically about inclusive DIS. In particularly, we know something about the rough size of power corrections, which in this case can even be partially computed. That's very nice. On this occasion, just comes back to my mind, I should make a compliment here. Why is it that I mention the unpolarized and longitudinally polarized quark distributions, but not the transversely polarized distributions, which Barbara has also discussed for the break? That is an important point, actually. The interactions of a photon with a massless quark conserves the quark helicity. And that means, if one does a little bit of Dirac algebra, that in this type of process, the quark transversity distribution, the transverse polarization of the quark cannot be probed as a matter of principle. The same is, by the way, true in inclusive DIS. And that brings us back to a question before the break. Why are the uncertainties on the ordinary quark transversity distribution, not its generalization here, but on the ordinary one, why are there so big errors? Well, one of the most important reasons for that is it's impossible to extract this kind of quantity from deep inelastic scattering. And deep inelastic scattering is the backbone of any PDF extraction still. If you take that backbone away, it's not surprising that it's much harder to get any extractions of transversity distributions, and that's what happens. So these decouple from the electromagnetic vertices because of a symmetry of massless QCD. So DVCS is good for what it can do, but one should not forget that it has its limitation. If you do DVCS on a proton target, you have exactly one combination of the quark flavors, namely with their weighted with their squared electric charges. if you can, in addition, get information on scattering on the neutron, of course not a free neutron that would decay before you can do the measurement, but on a neutron in a bound nucleus, then you have another linear combination of flavors, which comes from the fact that the d quark in the proton, which this here is meant to represent, is equal to the up quark in the neutron, and therefore now you have the 4, 9 over here and the 1, 9 there. So flavor separation from electromagnetic processes like DIS or DVCS alone is very limited. And on top, getting the gluons is very limited because they only come in via NLO, by the graph I've shown a little bit earlier here, as a correction to the leading order graph here, or via the scale dependence where gluons and quarks mix with each other. So that's the reason why meson production processes, like the ones I've sketched here, are so valuable. By looking at different mesons, you can look at yet different combinations of the partons. And if the quantum numbers of the meson allow, you have the gluon GPDs enter at the same order in alpha S as the quark distributions. And that gives you an extra handle on the gluon. On the other hand, it seems that there's nothing free in life. The theory description of meson production is seriously more difficult and less accurate than the one for DVCS. And that has different reasons. The meson wave function is another needed non-perturbative input here. And although there is something known about this distribution amplitudes, their uncertainties is quite severe. It turns out the alpha S corrections to the leading order graphs, they have been computed. They turn out to be much larger than the alpha S corrections in DVCS. And there are very strong arguments that also the 1 over q squared corrections, these power corrections, which we know barely, if at all, how to estimate, let alone compute, that they are more important at a given value of q squared in meson production. So there is a balance to be found between more information and bigger uncertainties. And in the end of the day, one just has to try and do one's best in both areas and see how one combines the information with a reasonable estimate of the uncertainties. Now, there is one last special aspect of DVCS, which is very interesting and neat, and that's what I want to discuss at the end now. DVCS actually has a competition at the level of the process amplitude. Remember, the overall process for DVCS is a lepton scatters on a proton, is deflected by a large amount, and then in the final state you have that scattered lepton, a photon, and a proton. Turns out you can make exactly the same final state by radiating the photon not from some charged part of the proton, but from the lepton itself. That has that leading order in QED, just these two graphs. And then the information about proton structure is just the electromagnetic vertex of the proton. And that is described in terms of the same Dirac and Pauli form factors that we discussed in connection with the GPD sum rules before. So we have a competing process, and that process, the good thing about it is computable because we know these form factors at low values of t with very high precision. And now, since these two types of contributions interfere in the amplitude, so you should sum in the amplitude overall, we have a way to get not only the size of the scattering amplitude, but also its quantum phase. So that means we have a way of getting separately access to the real and the imaginary part of the Compton scattering amplitude. And remember, in the GPD language, the real and imaginary part come here with different types of convolution. The real part is a principal value integral of these fractional kernels. And the imaginary part at leading order here, if you pick up the imaginary part of this and that, I showed that on the slide last time, this gives you the GPD at the point where x is equal to c. So it's very nice that this can then be separated by using, I find this analogy with optics very nice. You can think of this DVCS project as something like a diffraction experiment. You have an incoming, in this case, virtual photon beam that is diffracted on the system that you want to learn something about. In optics, that could be a crystal. And now what you then measure is the scattered photon from this experiment. If you have a reference beam of the outgoing photon with a known phase, and that would be the analog of the Bethe-Heitler process, then you even have phase information here. And that's great. And it allows us to extract very detailed information from DVCS. So if one now looks at the relative importance of the Compton and the Bethe-Heitler process, turns out it depends crucially on the kinematic region. And roughly speaking, if I take the ratio of the Compton part and the Bethe-Heitler part, the Compton part has a 1 over y squared. Y squared is this inelasticity variable that you would also introduce for DIS, and 1 over q squared, whereas the Bethe-Heitler process has a 1 over t. But 1 over t is not surprising. It just comes from the propagator of the exchanged photon here, which has virtuality t, because that's the momentum transfer to the proton. So this basic pattern means that at small values of y, the Compton scattering tends to dominate, and small values of y, if you look at this formula here, means at a given value of q squared and Bjorken x, that's what you get if you have a large value of the lepton-proton collision energy. And if you go to moderate or large values of y, then the Bethe-Heitler will become more important, because by construction, our GPD language is valid in the region where 1 over q squared is much smaller than 1 over t. So in other words, the Bjorken limit tends to always pull the balance towards the Bethe-Heitler part. Now, if you're in an intermediate region where these squared amplitudes are of similar size, then the best signal for the proton, sorry, I misspoke. If you're in a region where the Bethe-Heitler process dominates over VCS, then your best your best avenue to learn something about the Compton process is not by its squared, but by the interference term with Bethe-Heitler. And that's, as I discussed before, exactly the term where I can separate the real from the imaginary part. And that is done using various symmetries. Maybe one I can point out very easily. How can we filter out this interference term? The simplest way conceptually to filter it out is to reverse the beam charge. That is, if you have a measurement possible both with electron and positron beams, or both with muon plus and muon minus beams, if you take the difference of these cross section, what happens? Well, if you change the beam charge here, then since here you have one vertex, the sign of this amplitude will reverse. However, in the Bethe-Heitler process, you have two vertices with a beam charge, so reversing the beam charge gives you back the same. And that means the interference between that and that depends linearly on the beam charge, and that's how you can separate it out from the cross-section. And that's been done experimentally on the one hand at the Hera Collider, where both positron and electron beams were available, and on the other hand, in the COMPASS experiment at CERN, where one has both a positive and a negatively charged muon beam. And there's various other ways to filter out the interference term that have to do with polarization degrees of freedom, but this I will not discuss here for reasons of time. That brings me to the summary of today. Generalized parton distributions, if you think about factorization, they extend this very important concept from partially inclusive processes to completely exclusive ones. And they extend factorization from a factorization at cross-section level to factorization at amplitude level. And since exclusive scattering processes inevitably involve momentum transfer to your target, using this trick of the Fourier transform gives us a totally new way of probing the detailed structure of partons in the transverse plane. And doing the Fourier transform, you get very intuitive access to spatial distributions of partons, while still keeping in information about the longitudinal momentum fraction in the longitudinal direction. With that, I'm done for today. It's a little bit earlier than normally, but I think nobody will be terribly sad. Tomorrow, we will then come to TMDs and to double parton scattering as time allows.
A lot of stuff. Thank you very much, Markus. Very nice as always. So, questions, comments? Well, it's late and we are tired. I would have a few questions, but maybe I can ask one concerning this last slide, no, the first statement, and the validity of factorization in the VCS. Well, it exists a proof, no, a formal proof of factorization. Nonetheless, as you pointed out, that also Barbara did, it is valid in a specific kinematic range when Q squared is large enough compared to minus T, no?
Yes.
And the problem is that you cannot specify how big should be Q squared and how big should be T in this sort of qualitative relation. So in a sense, you are forced to decide a posteriori if it is valid once you have the data, or
yes and no. It turns out actually for DVCS in recent years, people have made a lot of progress in calculating power suppressed contributions.
Right.
Now, these are only part of the power suppressed contributions. They're of kinematic origin. So very loosely speaking, people have been able to go beyond the simple kinematic approximations that I explained you in the last lecture. Things like neglecting transverse components compared with large longitudinal ones. This type of corrections involve the same non-perturbative input, namely the same GPDs that we have in the leading power result. And therefore, by computing these corrections, you really have a predictive power. And you can then see how big they are. And it turns out in the most precise measurements today, which are made at Jefferson Lab, where unfortunately Q squared is quite limited, the estimates for the size of these corrections at not very small t are that they are really important. The good thing is if you have computed them, there is no reason to be scared. You can take them into account. And you should, as the next step, think about the corrections that you were not able to compute.
Okay.
So for DVCS, since it is in a way the simplest factorizing process and almost as simple as DIS, except that you have different initial and final states, the theory tends always to be the most powerful for higher order corrections, but also for power corrections. For mesons, I think one needs to totally change the approach there, and at best you can try and have some model for power suppressed effects and see what gets out of that, but inevitably the uncertainty in that and also the amount of debate is always bigger if you have to argue rather than being able to compute.
And the number extracted from HERA data concerning the Gluon GPDs and this JXI production, in that case, you would say that you are safe concerning factorization, or? I mean,
difficult to say. The important thing in that case, the more important thing I think is that there are many power corrections which will affect something like the overall size of the cross-section, but not its t-dependence.
Nice.
Yeah? So what will affect the t-dependence is the fact that the meson, the J-psi meson, is not really quite point-like. And that's what you would like to have. If the photon is real, it's not what gives you the small size of resolution power, it's really then the size of the J-psi meson. Now we know something like what the size of the J-psi meson is. It's rather small compared with other mesons, but it's definitely not point-like. So that puts you an uncertainty on that number, which I quoted, because the size of the J-psi meson, which in the leading power calculation is approximated to be 0, is going to give an effect on the t-dependence. Yeah. You can phrase it in a different way. If you have a probe of a certain intrinsic size, you cannot resolve any detail of your target that is smaller than the intrinsic size of your probe. Yeah. So this is very unsurprising that it happens like that. So yes, there is a limit in resolution in that case. And in fact, people have looked at this a little bit. If you are able to do the same experiment with an off-shell photon on top of the J-psi with its heavy quark probe, then the situation should rapidly improve. The cross sections become smaller, but the theory interpretation gets much cleaner. And that is one of the things which I hope will be possible at the EIC, where such rare processes with small cross sections can be measured with much better statistical precision than before.
Thank you very much. I'm happy with this answer.